Hello and welcome to this year's Wolfram Technology Conference. My name is Lucina Zukesan. I'm a kernel developer in the discrete computation team. So let's begin the talk. Today we will talk about data security and cryptography. We will explore one of the most widely used cryptographic algorithms, the RSA, and most importantly, how it relies on prime numbers for its security. Number theory has long been thought to be without many practical applications. The number theorist Leonard Dixon once said that thank God that number theory is unsullied by any application. And prominent British mathematician Hardy said, the theory of numbers has always been regarded as one of the most obviously useless branches of pure mathematics. But such a view is not true now. The significant increase in the availability and usefulness of computers in the 20th century drastically changed that situation. In 1974, Donald Newell said that virtually every theorem in elementary number theory arises in a natural, motivated way in connection with the problem of making computers do high-speed numerical calculations, and the best-known applications of number theory are cryptography and data security. What is data security? Data security is the protection of digital information throughout its life cycle from unauthorized access, corruption, and theft. It plays a crucial role in today's interconnected world where vast amounts of sensitive information are stored and shared across networks. Data security encompasses various strategies, technologies, and practices designed to ensure the confidentiality, integrity, and availability of data. The latter three are the core principles of data security and are usually referred to as the CIA triad. In today's digital age, data or cybersecurity threats are becoming increasingly prevalent and sophisticated. From malware to phishing to ransomware, there are various types of threats that can compromise the data, including hacking, data leakage, negligence, fraud, theft, and even natural disasters. These threats can lead to financial loss, data breaches, and identity theft. To combat these threats, strong security measures are crucial. We talked about the CIA triad. Today we will mostly focus on the confidentiality dimension, so let's learn about them starting from the availability aspect. Data availability ensures that systems, networks, and data remain accessible to authorized users when needed. What it means: accessible systems, ensuring that systems, networks, and data are always accessible and functioning correctly. Business continuity, preventing disruptions from cyber attacks, hardware failures, or natural disasters to maintain ongoing operations. And timely access, providing reliable and timely access to information when it is needed. The next dimension in the CIA triad is data integrity. Data integrity is the assurance that data is accurate, complete, and consistent over time. The key aspects are accuracy. Data is correct and free from errors. Completeness. All necessary information is present. Consistency. That means that data is uniform across all systems and sources. Reliability. That data can be trusted to be accurate and complete over time. And of course, authenticity. Data has not been altered in an unauthorized way. And finally, data confidentiality is a set of rules that limits access or places restrictions on any information that is being shared. How can it be maintained? Here are some of the effective ways to ensure it. Access controls, that is, restricting data access to authorized users through authentication. Encryption, scrambling data to make it unreadable without the correct decryption key. Secure protocols, using secure connections to protect information as it moves between systems. Data masking, that is, using techniques to hide or alter sensitive information. And physical security, that is, protecting the physical devices where data is stored. As can be seen, encryption is one of the key aspects in ensuring data confidentiality. It secures information by converting it into a coded form that can only be read with the right key. This process is rooted in cryptography, the broader science of designing mathematical techniques to protect and verify information. Cryptography is the practice and study of hiding information, which means codifying a message to preserve its content from unwanted eyes. The goal is to convert messages in a way that makes it hard to decode them. A scissor cipher, also known as the shift cipher, for example, is one of the simplest and most widely known encryption techniques. Let's take a look here. Here is the ciphertext, and here is the decrypted original text. The most dramatic shift in cryptography occurring in the final 2 decades of the 20th century was the adaptation of cryptography for the information age. Modern cryptography relies heavily on various mathematical fields. In cryptography, a key is a character string used in an encryption algorithm to transform data into an apparently random form. Data is encrypted like a physical key securing a lock, requiring a matching decryption key for access. We call the original data plaintext. The encrypted data is called ciphertext. Generally, there are 3 types of cryptography. Symmetric key cryptography, where a single common key is used to encrypt and decrypt messages. Asymmetric key cryptography, where a pair of keys is used to encrypt and decrypt information. And hash functions. This type of cryptography uses no keys. Symmetric key cryptography is a type of encryption scheme where the same key is used both to encrypt and decrypt messages. A shared secret key used by both sender and receiver can be a password, code, or a secure random string of letters or numbers. For example, Alice and Bob have agreed on the cipher and the key to encrypt their future messages. Alice uses the key to encrypt the plaintext and sends the ciphertext to Bob. And then Bob has the same key and uses it to decrypt the message. Encryption and decryption are essentially an inverse of each other, which is the reason why this type of cryptography is also called symmetric cryptography. Symmetric algorithms allow for messages to be encrypted and decrypted quickly. However, there is a significant disadvantage. In symmetric key cryptography, both the sender and receiver share the same key, and they have to somehow exchange the key. Sharing keys over unsecured connections risks malicious interception by third parties. If they gain access to a specific symmetric key, the security of any data encrypted using that key is compromised. If you could find a method of encryption-decryption such that exchanging the keys does not reveal how to decrypt intercepted messages, then you would avoid this problem. Using such a system, messages are encrypted with the receiver's public key, and only their private key can decrypt them. In an innovative paper from 1976, Whitfield Diffie and Martin Hellman introduced a new type of cryptographic system that uses 2 keys. 2 different but mathematically related keys are used, a public key and a private key. The public key may be freely distributed and is used for encryption. The private must remain secret and is used for decryption. This type of crypto system is called asymmetric or public key cryptography. This system is so constructed that the calculation of the private key is computationally impossible from the public key, even though they are related. For Alice to receive messages encrypted with an asymmetric cipher, she needs to generate a key pair and send her public key to others. Bob and anyone else who has Alice's public key can now encrypt messages for Alice. And Alice can decrypt Bob's message with her private key. There are many public key algorithms. One of the most important ones is the RSA. The RSA is entirely based on number theory, particularly modular arithmetic, and its security relies on the computational difficulty of factoring large numbers. It's a simple yet reliable and elegant algorithm. Although the concept of an asymmetric public key crypto system was first proposed by Diffie and Hellman, they did not present a completed algorithm, perhaps because the difficulty of factoring was not well studied then. At the MIT, Ron Rivest, Eddie Shamir, and Leonard Edelman were working to create such an algorithm. Finally, in 1997, they publicly described the algorithm, which is known as RSA. The RSA algorithm has 4 steps. Key generation, that is, 2 pairs of keys need to be generated, a private key and a public key. Key distribution, the exchanging parties need to know each other's public keys. Encryption, the sender has to encrypt the message using the public key of the receiver. And of course decryption, the receiver has to decrypt the message using his or her private key. So, key generation. To get a private and public key pair, choose two distinct large prime numbers, P and Q. Important to note that P and Q are kept secret. Now compute their product N. N is used as the modulus for public and private keys and is released as part of the public key. Now compute the Carmichael-Tauchiant function for N. It is a difficult computation in a general case. However, with the knowledge that N is the product of P and Q and that P and Q are prime, it's very simple. It equals to the least common multiple of P minus 1 and Q minus 1. Lambda is kept secret. Now choose a public exponent, a number e between 1 and lambda, co-prime to lambda. Conventionally, a prime is chosen here because it has no divisors other than 1 and itself. So you only need to check if lambda is divisible by the chosen exponent e. E is released as part of the public key. And now compute the private exponent d, which is equal to the modulo multiplicative inverse of e modulo lambda. D is kept secret as the private key exponent. Done. Now we have generated the keys. The public exponent e and public modulus n are shared with others, while the private exponent d has to remain secret. After the key pair is computed, all the future encryption and decryption is simply modular exponentiation. Here we implemented the RSA only for integers, so to be able to encrypt text messages, we will simply need to define a conversion between strings and integers. Here's an example. Encode the plain text into an integer, encrypt it with the public key. Now decrypt it with the private key, and decode the integer back to text. There you go. Security of RSA. So as you now know, it all starts with the selection of two large primes, P and Q, and the product of these primes is the public modulus. Apart from computing the modulus n, the prime factors are also needed when you try to compute the Carmichael-Tauchiant function lambda for n. Without the knowledge of initial factors P and Q, given only public modulus n, it is a computationally infeasible operation for big values of n. However, knowing prime factors P and Q, you can compute lambda and the private exponent d easily and instantly. Here, let's choose a particular default value for e recommended by cryptographers. So the pair NE is the public key and D is the private key. It is important to understand how the RSA crypto system remains secure after making the values for N and E public. In general, if an outsider wanted to attack an RSA cipher, they would have to find the value of D. However, if the primes P and Q are large, knowing the public key NE would not be enough to determine D. And we already showed that, so in order to determine D, one would have to factor n to find P and Q so that lambda could be determined, something that would be practically impossible if P and Q are both hundreds of digits long. And so the RSA security is based on the difficulty of factorization of n to get P and Q. And for this reason, the initial factors P and Q have to be kept secret, and in practice are often destroyed right after creation, since knowing one of them makes computing the private exponent trivial. And so we have finally arrived at the importance of prime numbers in the RSA. The key to achieving a high level of security for RSA ciphers is to choose P and Q to be very large. The larger P and Q are, the more difficult it becomes to factor n. That is, the RSA cipher's high level of security is due to the difficulty of finding P and Q from factoring. In modern implementations of the RSA cipher, it is required that the prime numbers P and Q should be at least a couple hundred digits long to ensure the security of the cipher. But prime numbers are scattered randomly throughout the number line. In other words, there is no pattern of prime numbers among composites, and determining whether an integer is prime or not is an age-old problem. It is very challenging to efficiently generate prime numbers. But there do exist methods for generating primes or for actually determining the primality of a number. Let's learn about prime sieves. A prime sieve works by creating a list of all integers up to a desired limit and progressively removing composite numbers until only primes are left. A prime sieve is a fast type of algorithm for finding primes. There are many prime sieves. For example, the sieve of Eratosthenes, the sieve of Sundaram, the still faster but more complicated sieve of Atkin, and various wheel sieves. These are efficient methods for determining small primes, but inefficient for determining primes that are hundreds of digits in length as desired for RSA ciphers. To show how sieves work, let's take a look at the sieve of Eratosthenes. It starts by marking the multiples of primes as composites. Let's find all the prime numbers less than or equal to 25. So first create a table of consecutive integers from 2 to 25. The first prime number is 2. Cross out all the multiples of 2 except for 2 itself. The second prime number is 3. Now cross out all the multiples of 3 except for 3 itself. And then next prime number is 5, and now cross out all the multiples of 5 except for 5. So the next step would be to cross out every seventh number in the list after 7, but they are all already crossed out. And so the remaining numbers are all primes below 25. So, sieves are inefficient for determining primes that are hundreds of digits in length, as desired for RSA ciphers. To generate large primes, the mainstream method is to generate random numbers in a target range and test them for primality using primality tests. A primality test is an algorithm for determining whether a number is prime or not. There are two types of tests: probabilistic and deterministic. A probabilistic test attempts to determine whether a number is prime or composite. The output of the test should be correct with high probability. They are much faster than deterministic tests. The simplest probabilistic test is the Fermat test. The Miller-Rabin is a more sophisticated variant. A deterministic test outputs true when the number is a prime and false when the number is composite, with probability 1, so it determines with absolute certainty whether a number is prime. The AKS primality test is the most efficient deterministic primality test known to date. To this day, the RSA cipher is still considered to be an unbreakable cipher and a secure form of communication. However, advances in technology, specifically quantum computing, and further research into integer factorization techniques could pose a serious threat to the security of the RSA in the near future. New mathematical and AI-driven techniques are making prime discovery faster and more efficient, and improved hardware and randomness sources ensure that generated primes are truly unpredictable and secure. Also, advances in parallel processing and cloud computing enable rapid generation and testing of extremely large primes. And related to the future of cryptography, the focus is shifting towards quantum-resistant systems that no longer depend only on prime number properties. To conclude, let's revisit the main points we have explored throughout this talk. The CIA triad, confidentiality, integrity, and availability, forms the core framework of data security. Data confidentiality starts with cryptography. Prime numbers play a key role in modern cryptography, and security depends on how difficult it is to factor big numbers. The speed and reliability of prime generation are crucial for security. And the next era of innovation in data security and prime number generation is already unfolding.